Hello everybody, welcome to this Head Start to A-Level Chemistry video. In this video I'm going to be taking a look at the periodic table and something called periodicity. I'll be paying particular attention to Group 2 and to Group 7, focusing on the melting point and boiling point and the reactivity patterns as you go down the groups. We're going to start this video by taking a look at some of the really useful information that the periodic table holds. First of all, and very simply, there is a division between metals on the left-hand side and the centre and the right-hand side of the non-metals. And there's this sort of set of stairs that divides those two regions. And from that, you can work out quite a lot about what the elements will be like. Secondly, every element in the periodic table has its own symbol. The symbol always contains a capital letter. If it's a commonly used capital letter, we also have a second letter or occasionally a third, and those second and third letters will be lowercase only. Then if we look a bit more detail at some of the contents of the boxes, I do review this in more detail in my atomic structure Head Start video. All the elements have got what's called an atomic number. Typically that's shown at the bottom, but that is always an integer value, and it is always the smaller of the two numbers, with the exception of hydrogen, where both of the two numbers are the same. The atomic number tells us how many protons there are contained in an atom of a particular element. And in fact, it's that proton number that tells us what the identity of an element is. If it's got a different number of protons, it will be a different element. Protons have got a positive charge and are found in the nucleus of an atom. The atomic number of an atom also tells us how many electrons there are present orbiting the atom in the shells. The number of protons is always equal to the number of electrons for an atom. If that is not the case, it's not an atom, it's actually an ion. Additionally, all elements have got a mass number, which is the total number of protons and neutrons found in the nucleus. So in other words, you take the number of protons, you add the number of neutrons together, and that is where the mass number comes from. So if we consider fluorine, which has got 19 as its mass number, that means the number of protons add the number of neutrons makes 19. Now it's also got the atomic number of 9, meaning 9 protons, so we can deduce that there must be 10 neutrons because 19 take away 9 gives us 10. This mass number, which obviously must always be the larger of the two numbers, is also sometimes called the relative atomic mass. Now, strictly speaking, those two aren't the same quantities. The mass number is always an integer because it is always protons add neutrons. The relative atomic mass is actually an average value of all the masses of all the isotopes of a particular element, taking into account how abundant each of those isotopes are. So that doesn't have to be a whole number value, and in fact, one of the biggest differences between the GCSE periodic table and the A-level periodic table is that all elements are shown as having an extra decimal point for their relative atomic mass. So sometimes it will be 12.0 for the relative atomic mass of an element, but other times it will have an extra decimal point, 32.1 for instance, that just wouldn't have been displayed on the GCSE periodic table. Just like at GCSE level, you get a periodic table in the A-level chemistry exams, so you don't need to learn any names or symbols. And in fact, you do end up using it in a very similar way to at GCSE level, except maybe the biggest difference is that you might have fewer marks for a task that you would have got at GCSE level, or maybe you're going to be required to go into something more deeply at A level and perhaps build on something that you can derive from the periodic table, but apply it to an unfamiliar situation, and that's where you'll get the marks in the A level question. For instance, you need to know that the groups of the periodic table are the columns. That means they go up and down. And they have numbers, they are numbered left to right, so this is group 1, group 2, etc., with the transition metals interrupting the number system in the middle. And then we have the periods, and they are the rows that go left to right, and they are numbered in increasing order as we go down the periodic table. We can use the groups to learn how many outer shell electrons a particular element has. That's called the valence electrons, the electrons that could be involved in bonding. Now, the pattern is very simple. All the elements in group 1 have one outer shell electron, and group 2, all the elements will have two outer shell electrons. The period number is very similar, except that the period that an element is in tells us how many occupied electron shells the element has got. And all the elements in the same period will have the same number of occupied electron shells. We can also use the periodic table to work out the electron arrangement, because we simply need to know how many electrons there are in the particular element, and remember that it goes 2 in the first shell, and that's coming from the fact that there are 2 electrons in the first row. It can fit 8 electrons in the second shell, 8 in the third, and then we get to element number 20, and the pattern gets quite complicated, and that's why we stop at 20 at GCSE level. If you want a little bit more of a taster about how electron arrangements work at A level, check out my atomic structure head start video. Also, we can use the periodic table to work out a formula or to deduce what type of bonding will be present in a compound. I go through that in my covalent compounds and ionic compounds head start videos. We can also use the periodic table to predict properties that elements might have, and we'll look at that now, focusing on group 7, the halogens, which we encountered at GCSE level, and group 2. We looked at some of the elements found in group 2, but you need to know a lot more about the patterns at A-level chemistry, and we will get a head start with that here. The periodic table gets its name from the word period or periodically. Now, periodically means something happens at regular intervals quite frequently. Using the periodic table to explore the world around us is often referred to as periodicity. Now, periodicity is the study of patterns that repeat themselves at regular intervals. Typically, when we're talking about periodicity, we're talking about patterns across a period, or, as we're going to look at now, down a group. One of the most common patterns that we look at is reactivity, so we're going to consider that first. So what affects the reactivity of an element? Usually when we're talking about the reactivity of an element, what we're really considering is how readily does it form ions. Now, if you remember, ions are formed when elements lose or gain electrons, and this involves electrostatic attractions either being broken or formed. So when considering what the pattern will be in a particular group, what we need to do is we need to first consider what do the elements of that group need to do to get a full shell of electrons. And so the consideration part 1 is, well, first of all, are they metals? What metals do to get a full outer shell of electrons is they lose their electrons. So the most reactive metals will be the ones that lose electrons more easily. And so the question really becomes, which element in this particular group, whether it's group 1 or group 2, which one loses the electrons most easily? And that comes down to the electrostatic attractions, as we'll explore in a moment. And then similarly, we've got the non-metals over on the right-hand side. Well, they need to fill their outer shell by gaining electrons. And so the question becomes, which of these elements gains the electrons more easily? Again, this is to do with electrostatic attractions. If we consider first group 7, the halogens. Now, being in group 7, they've got 7 electrons in their outer shell, so they need to react with a different element in order to attract an extra electron from another atom, probably a metal. So the reactivity of the group 7 elements depends on how strongly the nucleus of that element will attract these additional electrons. And the stronger that attraction is, the more easily these extra electrons will be attracted, and the more reactive that element will be. So because the group 7 elements get larger as you go down the group, that means they've got more electron shells, the positive charge of the nucleus will be blocked or shielded from the outside world. And that means that the electrostatic attraction from that nucleus for these extra electrons that the elements are trying to attract will decrease as you go down the group. So what that means is that fluorine will be the most reactive group 7 element that there is, and then chlorine will be slightly less so, etc. as we go down the group. Don't be surprised if you get asked about something like astatine, even though you've never studied past iodine. That pattern continues as you go down the group. Potentially, this could be a 3-mark question, and you would need to say the reactivity decreases down the group because electrons are gained less easily because there is a weaker electrostatic attraction from the nucleus for the additional electron, and that comes down to the increasing size of the atom as we go down the group. You can do a series of chemical reactions to prove this pattern in reactivity, and these are called displacement reactions. What you do is you mix a halogen, for instance chlorine, with solutions that contain halide ions. So for instance sodium chloride, sodium bromide, sodium iodide. And then if the halogen that is being added is more reactive than the halide ion that is already present in the solution, we will get a displacement reaction. So for instance, in the example that I've outlined here, the chlorine is the most reactive of these 3 halogens that are present. So when you add it to the sodium iodide, the iodide will be displaced and we will form sodium chloride, and we will make iodine as a byproduct, and we will see the brown colour of iodine forming, and that's proving to us that a reaction has occurred. Because sodium iodide has no colour, chlorine in the concentrations that we work with in a lab doesn't have any colour either, and so the formation of the brown colour is proof that a reaction has occurred. Then the reaction where we add chlorine to sodium bromide, we would see a yellow coloured solution forming at the end. And that's because bromine has been formed, because the bromide has been displaced. And this is again proving that chlorine is the more reactive. Now, when you add chlorine to sodium chloride, nothing is likely to happen or be observed because chlorine and chloride, there is no difference in reactivity there. So you would expect no visible change to occur. So this series of chemical reactions can be repeated, only this time you add bromine to sodium chloride, sodium bromide, sodium iodide, and you'd only expect one reaction because bromine is more reactive than iodine. If you repeated it with iodine adding to the 3 different sets of solution, you would expect no positive results at all, proving that iodine is the least reactive of these 3 halogens. The halogens all form diatomic molecules. That means that they share electrons in a covalent bond and that the elements go around in pairs, so F2, Cl2, Br2, I2, etc. And you can see this by drawing a dot and cross diagram as I've got here for fluorine. Now the elements will have different boiling points depending on how easy it is to separate molecules of this substance from each other, and this depends on how strong the attractions are between these molecules, or in other words it depends on the intermolecular forces. Now I go into intermolecular forces in greater depth in my covalent compounds video, but to give you one little bit of it here, the larger a molecule is, the stronger the intermolecular forces will be. And as I've already said, the atoms in a halogen get larger as you go down a group, so then the molecules that they form will also be larger. And so fluorine, F2, will be the smallest halogen molecule. And so that means that its melting point will be the lowest and its boiling point will be the lowest. And both of those things will increase as we go down the group. Not only do you need to know this pattern, you also need to be able to use it to justify the states that you find the halogens in at room temperature. So that means, are they a solid, are they a liquid, or are they a gas? One of the many things that are interesting about the halogens is that actually it is the only group in the periodic table that contains all 3 of the typical states that you find elements in. Fluorine is a gas because its intermolecular forces are really weak. Same for chlorine. Now, when you get to bromine, the intermolecular forces are stronger. They're strong enough to prevent the bromine from evaporating, from turning into a vapor, but they are not so strong that they prevent it melting. So bromine is a liquid at room temperature. The intermolecular forces in iodine are so strong that iodine is a solid at room temperature. There isn't enough energy to overcome those forces and make the iodine melt. The last thing that I want to remind you of about group 7 is that you need to be able to know how to test for the presence of particular halide ions. Now, to do this, you use a chemical called silver nitrate. You also use an acid, so it's often called acidified silver nitrate. When you do this reaction, what you get is you get precipitates forming. Now, precipitates are insoluble solids that form during the reaction of two solutions. The precipitates that form here have got distinctive colours. You make silver chloride if chloride ions are present, and that's a white precipitate. You make silver bromide if bromide ions were present. That's a cream precipitate. And you make silver iodide if there were iodide ions present, and that's a yellow precipitate. The purpose of acidifying the silver nitrate is to prevent the formation of misleading precipitates, because carbonate ions, for instance, also react with silver to make white precipitates. And so what the acid does is it reacts with the carbonate ions and uses them up and converts them into water and carbon dioxide and stops the formation of that misleading white precipitate, which means that if you see a white precipitate being formed, you can be confident in your conclusion that chloride ions were present at the start of the reaction. Just in case you wanted extra confirmation, because a white precipitate and a cream precipitate can look quite similar, certainly if you don't have both of them, you might not know whether it was white or cream. What you can do is you can add a further chemical, dilute ammonia solution, and what that will do is that will dissolve the silver chloride. And so if you get a white precipitate that then dissolves if you add dilute ammonia, then you know that you started with chloride ions present in your solution. If we move on now to take a look at the elements of group 2, starting with their reactivity, remember that these are metals, so as you would expect from metals, they are going to be giving away their outer electrons to fill their outer shell, or to make an inner shell kind of become the outer shell. In order to donate those two outer shell electrons, something else needs to take them and overcome the attraction between the nucleus and the outer shell. Now, this attraction will decrease as the atom gets bigger. And that means that beryllium will be the least reactive group 2 element, magnesium slightly more reactive, calcium slightly more, etc., as we work our way down that group. And so, if you were given a 3-4 mark question to answer, you would say reactivity increases as you go down group 2 because the atoms become larger, the electrostatic attraction between the nucleus and the outer electrons decreases, so the electrons are lost more easily. Really similar to the answer that we gave for why the halogens become less reactive as you go down group 7. Only a few words different, kind of switched out for their opposite. So I recommend that you really concentrate on learning these 3 or 4 mark answer explanations. If we take a look at the melting points of the group 2 elements, you can see that broadly speaking, the melting points decrease as you go down group 2. Obviously, the group 2 elements are all metals, so what that means is that the metallic bonding gets weaker as you go down group 2. Now, metallic bonding is an electrostatic attraction between a lattice of positive metal ions and the delocalized electrons. So what that means is this electrostatic attraction must be weaker for barium than it is for beryllium, and this is down to the size of the metal ions. The size of barium is significantly greater than the size of beryllium, and that means there is a weaker electrostatic attraction because the charge density of the barium ion is much, much less than it is for the elements higher up in the group. And that charge density decreases as you go down the group, and the electrostatic attraction decreases as well. We can see that magnesium is an exception to this, which tells us that the pattern can't be quite as clear-cut as I've just said, and it isn't. Not only is it to do with the electrostatic attraction, as I've mentioned, it's also to do with actually the separation of those ions in their solid kind of crystal structure, their three-dimensional lattice. They aren't all equally spaced out in their lattice. Sometimes the ions are a bit further apart than others, and that means that kind of less energy needs to get put in to separate them a bit further. And that's thought to be the case for magnesium, and why magnesium is easier to melt than its position in the periodic table would suggest. Something else from GCSE chemistry that you need to know about group 2 metal ions is that they react with sodium hydroxide. In fact, that's one of the chemical tests that you needed. You add sodium hydroxide to a solution thought to contain metal ions, and you get a coloured precipitate depending on the ions that are present. Now, the two that you needed at GCSE level were magnesium and calcium. Now, both of them actually give a white precipitate. So at face value, it's kind of hard to tell them apart. But magnesium forms much more of a precipitate than calcium. What this tells us is that the magnesium hydroxide that forms is very, very insoluble. Whereas for calcium, even though we get a white precipitate, we don't get so much. And that's because calcium hydroxide is more soluble than magnesium hydroxide. And so you get less of a precipitate. When it comes round to strontium and barium, you don't get a precipitate at all. And that's because those two hydroxides are completely soluble in water. You can actually distinguish between the calcium and magnesium beyond this chemical test method. The way that you do that is you use something called a flame test, which is where you introduce a sample of this metal ion to a blue flame of a Bunsen burner, and if you get a sort of a brick red colour, then you know that you've got calcium 2+ ions present. Whereas if you don't, you have basically no additional colour forming, then that is suggesting that it was the magnesium that was causing that white precipitate, because magnesium gives out energy in a flame test that's outside the visible range, so our eyes can't detect it. You can also use group 2 elements to test for the sulfate ion. And the way that you do that is you add barium chloride solution in the presence of an acid such as hydrochloric acid, and if sulfate ions are present in your unknown sample, you will see a white precipitate forming. And that's because you've made barium sulfate, which is insoluble, and so that is the identity of the white precipitate. And in fact, barium sulfate's got medical applications. It's used in something called a barium meal that you take before an X-ray, so you drink it and it coats the inside of your intestine and makes it what's called photoopaque, which means that the X-rays can't pass through the intestine and they show up in a similar way to bone does as you take your X-ray scan. If you were to try using any of the other group 2 metal ions to test for your sulfate, it just wouldn't work. Beryllium sulfate, magnesium sulfate, calcium sulfate and strontium sulfate, they are all soluble in water. And one last thing to say about the sulfate ion test. If you can use barium ions to test for the presence of sulfate ions by mixing the two of them together, then it works in reverse. The sulfate ions can be used to test for the presence of barium ions. So if you added something like sulfuric acid to an unknown solution and you got a white precipitate, you can be reasonably confident that your unknown solution contained barium ions in the first place. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.